Yes, and I'll apologize in advance for the internet connection I'm on. I'm in a hotel in Washington, D.C., and the bandwidth is not great. So hopefully it won't lag on me too much. So what I'm going to talk to you about today is a space mission that we're putting together called PolStar that will be proposed under the NASA Explorer opportunity at the end of the year. And the mission is a far ultraviolet spectropolarimeter to primarily address the life stories of massive stars through a variety of observational techniques, but it goes beyond that to address issues in the interstellar medium and with exoplanet formation as well. The people who are putting this mission together are on the screen there. Myself, Rico Ignas, who's the deputy PI, Ken Gailey is the project scientist. Woody Woodruff is the optical designer who's responsible for about half the instruments on the Hubble Space Telescope right now. We're using a lot of design innovation that Coralie Niner has brought to the table, which is based on things that she did with her Arago proposal and with the Pollux instrument that was proposed as part of the LUVOIR concept. And then we are working with our partners at Lockheed Martin, who are bringing a number of technological innovations from the heliophysics world to provide us information and capability for stellar astrophysics. And our telescope designer is Tony Hull. So the mission itself is a 60-centimeter telescope with a 2-channel spectropolarimeter that covers the band from 122 to 320 nanometers. One is high resolution, one is low resolution. I'll look at that. I'll talk about that shortly. But the primary science areas are to understand and study the impacts of environment on the evolution of massive stars, and to look at questions concerning interstellar medium and exoplanet formation. We are working towards proposing this thing at the end of the year, and it would fly in 2026 if we were lucky enough to be selected. So one of the primary mission goals is to look at the impact of environment on the life story and evolution of massive stars. Massive stars, of course, in terms of the context of the baryonic life cycle, are the most important contributors to galactic cosmic evolution in terms of energy, material transport, and chemical evolution. They regulate the rate at which stars and planets form, and they intimately affect the ecology of material that flows through the cycle that's portrayed on the right-hand side of this particular slide. And so the questions we're seeking to address are: how does the environment and the changes to the mass loss, the capability that an actual massive star has to lose mass in what is now understood to be a very anisotropic process, how does that actually impact the rate at which these stars can potentially evolve? We're building this mission to address a whole series of strategic goals that were expressed by the last decadal survey issued by the National Academy of Sciences here in the United States. And the first set are looking at the effects of rotation and magnetic fields on stars and their mass loss and rotation rate and distribution of material, loss of angular momentum, that kind of thing. But also to look in the interstellar medium context at how magnetic fields and how energization aligns dust grains in the interstellar medium, and what that means for the conditions in clouds and other areas where dust is an intimate part of the ecology there. So the kinds of issues we're seeking to address in a massive star context is to look at things like how the influence of magnetic winds could change the mass loss rates and the angular momentum that is distributed in slow versus fast rotators. We're going to look at the rate at which material is actually dumped off of stars in potentially smooth and clumped stellar winds, and what that means for the distribution and the success of the mass loss mechanism itself. We're going to look at rotation in terms of critical rotation, core contraction, and binary mass transfer. One of the big factors, of course, is that half the massive stars in the night sky are in binary pairs. So we need to understand how the interdependence between two stars in such a system affects the way those stars can potentially evolve. We're going to look at the conservative nature of mass transfer in binary systems to understand how the intimate nature of those systems affects that rate, and to look at the constraints that are imposed on the strength of a stellar wind from a close companion. We're also going to be using techniques both in the Zeeman and in the Hanley effects derived from analysis and work that's been done in the heliophysics world to look at a better constrained idea about how magnetic fields alter the wind in strong wind magnetic stars, which is about 10% of the massive stars we see in the night sky. In the world of the interstellar medium, we're going to be looking at clarification and identification of alignment mechanisms for the smallest interstellar dust grains, looking at the wavelength dependence of the polarization that we observe in the ultraviolet. We're going to be looking to see how the Super-Sikowski effect in the ultraviolet polarization is characterized and shaped by looking at EUV illumination of those grains. We are, of course, going to be working in the near ultraviolet to try and gain insight into the 2175 angstrom bump to look at the polarization of this feature across a variety of environments. And we're going to be looking at the interstellar medium between us and our nearest galactic companions in the Magellanic Clouds to look at the nature of the polarization of the medium in that particular context. The other area, of course, is that we have some leverage in is looking at protostellar disks and to look at the mechanisms by which exoplanets are formed, to look at a variety of different theories and ideas concerning the transport of energy and mass in the inner disks and how that affects the formation of planetesimals and potentially evaporating bodies, and to look at ultimately how the atmospheres of those planets can be shaped by the environment within which they actually form. We're also going to use, of course, the magnetic signatures and to understand how the magnetic activity of the central star intimately affects the way those exoplanetary systems can form and what it means for the formation and retention of atmospheres on exoplanets and what that means for ultimately for habitability. So what do we need to do this? We need ultraviolet access. Of course, we have to be in space to do this. There's a whole series of diagnostic lines in the far ultraviolet resonance lines that allow us to map the wind and magnetospheric zones around these stars and to look into the media around protoplanetary systems, for instance. We need access to polarimetry, and we're going to be doing this. I'll describe briefly the instrument to you shortly, but we're going to be looking at using polarimetry as a diagnostic for magnetic field shape and strength to look at stellar rotation, mass loss, and a variety of other parameters. We're expecting to deliver signal to noise of about 1,000 at about 0.1% per exposure, a factor of about 100 for detailed spectroscopic studies. This thing isn't just a polarimeter. But we're also going to be stacking some of these signals to help us to achieve even better polarimetric accuracy as we combine a series of different observations. But one of the things that we're seeking to address with this is access to the time domain. A lot of the targets we're going to be looking at will be rotating under our line of sight. So that means that over time, we'll be able to build three-dimensional tomographs, not only of the wind structure, but also the magnetospheric structure, and to look at the evolution of the systems over time and give us information about the way mass loss and the nature of the winds varies as a function of time. The data we're going to get out of this, we're going to be doing this using a rotating modulator with a set of 6 individual observations per sequence. Each one, of course, is going to produce a spectrum. Our spectrograph on channel 1 is going to deliver a spectral resolution of an R of 30,000. And we'll be conducting and measuring polarization for each set of sequences, providing spectral data to produce line profiles, line strengths, kinematics, densities, temperatures, and abundance information. So we'll be, for each target, we'll be measuring I, Q, U, and V, also a function of time and a function of wavelength. Calibration, of course, will be done using a series of calibration lamps and external calibrators. And this is where RoboPol becomes critical to us. We're already working with collaborators and co-investigators, Gina Polopoulou and Andrei Bertigin, who spoke earlier, will be helping us with some of this. And we're seeking to add more blue targets to the RoboPol sequence because we believe that they're going to be critical to identify external sources that we can use to map and potentially look at any variants in our polarimetric sensitivity and calibration as the mission goes on.
All 5 minutes.
Thank you. Flat fueling the system. We're going to have an internal lamp, but we also are seeking to find sources external. There are a number of particular white dwarf sources that the Hubble Space Telescope has used for this purpose, and we'll be looking to do that as well. So this is the design of the instrument. Many aspects of this were addressed by Andrei's excellent talk earlier today. The telescope, of course, has to be completely symmetric, so it does pick off at the Cassegrain focus. It goes into a single point source entrance aperture, goes through a rotating modulator that are a set of mag fluoride crystals that are rotated to those 6 positions. This is using technology development that Coralie Niner has developed in Paris. Then, of course, there is the Wollaston prism, as you've seen both in Andrei's and Siddharth's presentations today. There are 2 channels. The high resolution one is the channel 1 that provides a collimation mirror that feeds off an shell, and a cross disperser to map the wavelength regime of 122 to 200 nanometers to our ultraviolet enhanced detector. The second channel, which uses a pickoff mirror, then feeds the beam through a mag fluoride prism to produce a much lower resolution, R of 20 to 90, across 180 to 320 nanometers onto the same detector. A lot of the technologies that have been brought to bear here have been developed in the last 5 to 10 years. We've had dramatic improvement in ultraviolet reflectivity of mirror coatings of detectors of the kind that we're baselining here, but also, of course, the technology development I mentioned by Coralie and her group. The PolStar instrument will provide a remarkable advance in what has been flown in space before in the ultraviolet. Orders of magnitude improvement, both in channel 1 and channel 2, both in the spectral resolution delivered and the effective area, even for the more modest 60 centimeter aperture that we'll be using. It will be, in fact, the first far ultraviolet spectral polarimeter to be flown in 30 years. It will measure all 4 Stokes parameters, both linear and circular, and will be a powerful successor to those earlier projects. So our mission will provide new insight into the evolution and life stories of massive stars, which shape the evolution of galaxies and produce the building blocks for stars, planets, and life. It's going to provide new information about the mechanisms that drive dust alignment in the ISM and the formation of exoplanets. And it's going to open up a space-based access to far ultraviolet spectral polarimetry, where we have not had this for quite a very long time. It is responsive to decadal survey priorities and fits within the cost cap, within our best estimates at this time. It is a strategically valuable mission within the metrics that NASA has self-identified, and it is a unique opportunity to bring together techniques from both the heliophysics and stellar astrophysics world to provide an interdisciplinary solution. With that, I'll pause for questions. Thank you.